All right, so let's look at the influence line for the shear at C. Now, if I were to cut the beam here at C to find the internal shear, let's just decide right now, do you want to work the left side for our equilibrium or the right side? I think the left side would be best. So in order to do that, I need to find the influence line for the reaction at A. So that's what I'm going to do first. So I'll actually come over here to the side and say, let's find the influence line for AY. So I'll redraw the beam. I'll put my unit load at some position X on the structure. And there's AY, and there's BY. I won't worry about the X reaction at A. And this is a total of 12 feet. So I want to find AY. How do I find AY? That's right. So I'll sum moments, right, using right-hand rule as my sign convention. I'll sum moments about B and make sure it's in equilibrium. Now, since I'm going from B, I need to know the distance from B to the load. What will that be?
12 minus X.
Right, 12 minus X. So when I'm summing moments about B, my unit load here creates a positive moment with a moment arm of 12 minus X. And then AY creates negative moment with a moment arm of 12. So solve for AY. AY is going to be 12 minus X divided by 12, which is really 1 minus X over 12. So I could plot that, and that would give me the influence line for AY. Mr. Abney.
So when you're doing the influence line for AY, that is simply the reaction forces for AY, kind of how we did shear moment functions.
Exactly. So if we plotted that, AY as a function across the beam, and the beam is 12 feet. Plot that. So when X is 0, what do you get? 1. When X is 12, what do you get? 0. And it's linear, so you should get a line that looks like that. So that means if this is me walking across the beam, where do I stand to create the largest reaction at A? At X equals 0, which is right on top of A. As I move away from A and walk over towards B, you can see my influence drops off all the way to 0. When I'm standing right at B, I'm creating no reaction at A. Okay? So we have that.
If you know it's symmetrical, could you swap it and say that's the influence line of BY? Does you know it's symmetrical?
Well, in this particular case, the influence line for BY would just be the mirror image of this. Because when you add AY to BY, at every point, what should they be equal to? 1. Right? Because AY plus BY better balance 1 for equilibrium. So I could find BY the same way. I don't really need BY right now. So let's do the influence line for C. So what I'm going to do, I have AY, so I'm going to draw my influence line, my free body diagram, and all I really care about right now is the shear at B, and I'm using that in the positive sense. What's my reaction at A? It is 1 minus X over 12. Thank you. Shear at C. Now in the first case, I'm going to assume my unit load is on this structure at some distance X with a value of 1. So this will be good for what? This will be good for a position X between 0 and 3. How do I find the shear at C? Some forces in the Y. So let's do that. I'll assume up is positive. So we'll sum forces in the y direction, make sure they're in equilibrium. So I'll start with what I have. I've got this force acting up, that's 1 minus x over 12. Then I have minus 1 acting down, and I have minus my shear at C acting down. So let's solve for the shear at C. And it looks like I get minus x over 12. Everybody see that? We'll just hold on to that right now. Now, let's look at the unit load as it moves off that structure and goes to the other section of the beam. But I'll still use my free body diagram from the right-hand side, because I still have what? My influence line for the reaction at A. I still have positive shear at C. But where's my unit load? It's over here somewhere. So it's not on this free body. Elvis has left the building, right? So I'll do exactly the same thing. I'll sum forces, assuming up is positive. Make sure are in equilibrium. And now what do I have? Well, I've got my 1 minus x over 12 force acting up and my shear at C acting down. So I can solve for shear at C as 1 minus x over 12. Now I just plot those things. So let's come over here, make a plot of the shear at C. Now before I had 12, now I've got to worry about this position 3. Yes?
I'm confused about the diagram when it's 1 minus x over 12.
The reaction, the influence line for A?
No, down in the free body.
Over here?
Yes. So I'm thinking like it's at 3. Why isn't it minus x over 12? We just got the shear at C.
Well, this is the shear at C when the unit load is between 0 and 3. Now, when the unit load is between 3 and 12, see, it's moved off the structure. The shear at C changes. Okay, it has to respond. Because now you see I have two different equations for the shear at C.
I was thinking that you were drawing the free body between 3 foot and 12.
No. Remember, x is the location of the unit load. This free body, I forgot this dimension. This free body is always 3 feet long. That doesn't change. That's probably what's messing you up a little bit, because you're thinking about you're cutting the section at a variable x and you're trying to find the shear and moment internally as a function of x. And we're not. We're finding the shear at C as the unit load goes from 0 to 3 and then from 3 to 12. The free body never changes. It just exposes the shear at C. Now I could get the same results if I'd have worked the right-hand side. It would just be a little more tedious on the algebra. So the left-hand side is just a little cleaner right now. So from 0 to 3, I have to plot this. So at 0, it's 0. And at 3, it's minus 1/4. And then from 3 to 12, I plot this. So I put in 3 here, and I get 3/4. I put in 12 there, and I get 0. So this is my influence line for the shear at C. One thing to notice is these slopes are the same, because this is the slope of the line, 1/12. 1/12. The slopes are the same. Also, I want you to pay attention to something too. What is this difference right here?
1.
Right. Is that coincidence?
Yes.
No. The load is 1. So as I start and I pass from the left side to the right side, I get this instantaneous change in the shear, and it's exactly equal to my load, 1. So what this says, Oh, first of all, let's answer the question. What's the maximum shear I can produce in the beam? Let's say that's me walking and I weigh, what are we in, feet and pounds? Let's say oddly enough, I weigh 1,000 pounds. What would be the maximum shear I would produce in this beam?
750 pounds.
750 pounds. It'd be the 1,000 times the 3/4. If direction were important and I ask you what's the maximum negative shear, what would that be? 250 pounds. And where would I stand to do that? Just to the left of C. Where would I stand to create the maximum positive shear? Just to the right of C. Cool, huh? Any more questions about that one? We'll work a few more of these. All right, I'll stop here.